I'm making a video. I want to get on the subject of electricity and magnetism, of course. It's always a kind of a side effect and charge. Just because I think I've got some of this stuff even tighter now about what happens in coils and all that kind of stuff and blah 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 blah, and even antennas and all that nonsense. But there's all these other peripheral subjects, and so this is sort of a, we'll leave it a draft video. I won't, I'm not proposing a final. I just figured it would be nice to talk through it, some of it, because some of these notions people have, even though they get something, they don't get other things quite obviously. So anyway, the Robert Ritchie made a video. I'll leave a link below. He's using this term "game on," which I don't really like, but it's not for me to like. Not a game in the first place. Not it's all I'm looking for is ways of testing what I'm saying against what other people are saying. It's all courtroom to me. It's not really a game. It's a trial, and the point is to demonstrate conclusions based on weak evidence, conclusions based on strong evidence, conclusions that are consistent with the evidence, conclusions that aren't consistent, ones that are broken for one reason or another. I mean, you can have something that's very strong evidence, like fingerprints, and then you could find out that your suspect doesn't have any hands, or some kind of crap like that, and you're like, oh, gee, that strong evidence just can't be worth anything, can it? That's kind of a broken example, but I just mean that sometimes, the strong evidence ends up being weak because it's inconsistent with another piece of strong evidence. Alright, so the subjects come up as Stern-Gerlach, the subject of spin, why I should believe any of this crap exists. So I've attempted to do some research. I can't find. So if somebody has can find some video somewhere of the experiment actually being performed, that would be nice. It's not that complicated. I don't know why there's not a single real video of it really happening. Just to see that the instrumentality is as they say, and what this deflection, blah 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 blah. But it has to do with basically they have a theory and they're modifying the experiment to fit the theory. Now I just kind of demonstrated, like I said, this I don't, Piro would argue that I'm somehow saying some of this stuff is malicious in some way. And of course I don't think it's malicious. Part of it I would say is like the Professor Lewin thing, okay, arguing that there's two voltages in one place. Stupid. And then totally ignoring the idea that, when you're using radio waves to do two slit experiments, you're going to have to worry about the idea of jamming is going to fool you. Just as scatter is going to fool you in looking at solar lensing, because you're not going to be able to see anything. You're not going to get enough bending outside of the corona to see anything anyway. And so clearly, the corona could be blamed for any deviations that exist in the path of the light. So these are real arguments, not fake arguments. And so as I sort of pointed out, this experiment where they're trying to essentially look for the motor force, the right-hand rule, and cause electrons to go up and down instead of what you would expect, which is away from or towards the magnet. And clearly I pointed out that, well, if you're at the right distance, you can get an illusion because of the bowl shape of the field that you're deflecting it down when you're really not deflecting it down. It's just rolling down the bowl, so to speak. So you can get you can make an experiment look a certain way, but that isn't the way it is. And I would argue that this Stern-Gerlach thing has that smell of an experiment that, well, what's all the variations of it? So you have this argument about this uneven field because you make a wedge out of the one pole of the magnet to make it really strong, and then I guess the other pole is weak, and so you have some sort of misaligned, I don't know it's still a consistent, it's still a filter, in the sense that it's not a linear perfect field. It's got angles to it. It's got some stuff to it. So why don't we know what happens to silver when you just put it through regular 2 magnets, normal magnets, no magnets? I mean, there's just little to compare anything to. And I would argue that the reason why there's so little is because it's all based on a premise, a thought experiment first, rather than an experiment first. So it was intended to demonstrate something rather than intended just to see what would happen. So they have this theory that there's no magnetic monopoles. They just assert it because Maxwell's equations don't, somehow imply something. But I don't even know how they can make the declaration. They just say it. When I can just as easily say, no, electrons are monopoles of magnetism. They're negatively charged. The proton is positively charged. I put the 2 things next to each other. I have a dipole and a magnet. I don't see any complexity at all. I don't see any violation of any rule whatsoever. And the idea, though, that something like an electron, because that's what they're doing with the Stern-Gerlach, they're speculating, mostly, that somehow electrons on their own have a dipole moment. When clearly I don't see how they could possibly have a dipole moment when they don't exhibit any dipolarity. They're not little magnets. They're clearly negative charge. They're clearly a north or a south pole of a magnet. They're not both. And likewise for the proton. So I don't even know why the conversation, well, I know why, but I'm just saying, so that's their assumptions. Their assumptions are everything's a dipole, when it's not, because they've declared there are no such things as magnetic monopoles. So somehow they have to make everything into a dipole and say it has some sort of spin moment where it's flashing its polarity at you. So I could understand if you're using neutrons or something, because yes, I would argue they're dipoles. You could spin one of those and you could have a dipole moment. Clearly an atom, a silver atom, as I understand it, has 1 electron in the outer ring. Clearly, when that 1 electron is looking at you, it looks more negative, okay, than when the electron's on the other side of the atom, it looks more positive. So clearly you could say those atoms have dipole moments if you give them any rotation at all. But again, this whole rotation idea, do they rotate when they're in a conductor? I would argue not. And so maybe after you've heated them and shot them away because with a bunch of radiation, maybe they're spinning as they go through this device. But again, I still don't even understand how the device filters for that spin in any particular way, and why it would have something to do with changing it from being, it could end up here, 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 to here or here. So I have to do some more thought to figure out exactly why they theorize that somehow this quantum effect is different than classical physics. They keep claiming that classical physics can't explain the experiment, when I don't even think they've tried to allow classical physics to explain. All right, so this is a lot on that. I'm probably never going to get to the subject I want to get to. So I have already made some statements, overtly. Okay, you can't force a force. So forces aren't going to interact with each other. Just isn't going to happen. Forget it. Okay, the stuff going the speed of light, if it interacts, it does so in a way that you can't tell the difference from it going right through each other or missing each other entirely. So what's the point? It can't do anything to change the strength or the presence of the force. So we're back to that word again that I keep, that just won't stay on the surface of my brain. Superposition. Forces can be added. You can add all the forces you want into a field, but you can't change the forces that are already there. You can't undo them in a force way. They have to actually hit the thing. You hit the thing with 10 pluses and you hit the thing with 10 minuses. You can't make the forces cancel first. All right. so you can't, and all right, so I'll read one of Richie's comments. I mean, his video, I didn't get much out of it. It was just this game on stuff, which I didn't really get. And again, talking about particles that I don't even believe exist as particles. So, you know, and functions that, yeah, I just don't, I see no reason for me to believe, because I see no evidence that these functions exist. All right, so it says, I propose that photon being deflected by the electron interaction in the slit. Okay, so now back to the slit experiment, which is, you know, another subject I wanted to get to, but I don't think I'm going to do it in this video. And material boundary interface. Well, that's one way to say it, but just surface is good enough. And you could say, well, maybe we could find some way. Material boundary interface, the boundary between two surfaces. That's what he's saying. So we need the boundary layer between two surfaces. It's a long sentence, but maybe that's what we have to call it. The photon is traveling towards the target, and as it passes an electron in the closest approach to the photon is traveling towards the target, and as it passes an electron in the closest approach to the photon. So let's see, again, this doesn't make any, that's not even a coherent sentence, so I can't do much with that. The photon has an affinity. No, it doesn't, for electrons. It just doesn't. The fact is, there's one mechanical function, okay? You know, I have to keep arguing. The photons we're talking about are photons made out of the same energy that reflects off electrons. So it's the electron force. That's what photons that we see, and that's the electromagnetic spectrum, is made out of those photons. It's electron reflexive energy. Now, the energy comes in both forms, the force, the proton force, but we have no examples of that having the same effect, because guess what? The protons are never in a position where jiggling them can make any difference. The electrons can be jiggled out of position. So thereby, that's why there's a difference. You can't, nucleuses are harder to break, a lot harder to break. All right. So, yeah, so you can't have a guided photon. The photon either hits the electron or it doesn't hit. It doesn't do flybys. There's no, the photons are gravity. So you're just not getting it. All the force bits come from one thing, the external universe. They're hitting everything from all directions all the time. And as they bleed into something, they can be converted into heat, or they can be converted into segregated black and red, which means magnetism. So they can be converted to other forces that we can recognize. But it's one force. It's all made of one thing, little bits moving the speed of light. And none of the bits have any special powers. Even when they're segregated, the little bits are the same little bits. They're little bits of with a capacity, the potential to impose momentum, depending on what kind of particle they hit, a proton or an electron. All right. The photon has an affinity for electrons. However, the angle of incidence is too great for the photon to fully couple. So these aren't languages I use, words I use. Doesn't couple. Clearly, the momentum is absorbed, so I guess it's a way of saying it, but I guess I just don't like that way of saying it. But let's just say it couples. The momentum is absorbed. It's trapped is my argument. Okay, so clearly what I'm arguing is that it's still moving the speed of light when it's in the matter. It's just trapped in circles or in back and forth or in some sort of trap. Lots of shapes the trap can have. And so it doesn't really couple. It gets trapped. So trap is the word I would use with the electron. And it can be trapped for a millisecond. It can be trapped for a day. It can be trapped for 10 million years. Just depends on the trap. And while it's trapped, the momentum is owned by the thing that trapped it. All right, with the electron. And the electron is also at the same time moving away from the photon. So no, it's just, I've said it as clearly as I can say it. Okay, the electron don't move until it absorbs, it traps a photon of some kind, a quanta of energy moving the speed of light. It has to trap it to move, and when it lets it go or loses it, falls out of its trap, it stops. That's it. Electrons have no capacity to move unless they have trapped force, unless they have got the rowers in the boat. All right. All right. Same time, moving away from the photon, which results in a deflection from a near coupling. There's no near coupling. There's no proximity. There's no bending. Because there's no gravity. Okay. Again, the photons are gravity. They can't bend because, like, they're in gravity. There's no second gravity that bends photons. So they can't be bent. They have to be absorbed and readmitted from a new position of momentum. So if they hit an electron, the electron moves to a new position, and then the electron decelerates. It'll shoot the photon from its new acceleration position. So if you understand what I've been saying, pretty much, when I say that this momentum thing comes in, it depends on what kind of tension the electron's under. If the electron is attached to lightly attached to a proton, then obviously the electron's going to move towards the proton as it moves in any direction. It won't go, its momentum won't be straight, just like the Earth is being bent by gravity. So that's really happening to the electron. The electron is being influenced by the field pressure, and so if I add a new piece of pressure in a direction, I'm not going to get a straight line out of the electron. And there go. If the electron is going to readmit the photon when it decelerates, so I give it some acceleration, it's going to move. It's not going to move in a straight line. So the momentum comes in this way, the electron moves this way, and then when it gives back the photon to the universe, it's pointed this way now. So the more energy I put in, the more arc, the more wild the angle that it comes out. So the stronger the gravity, that is, the closer the electron is to the surface of the proton, the closer it is to the proton, the higher the angle is going to be for any momentum in, and the more likely it is you're going to get a higher angle out when the electron stops moving and re-releases the energy. Now, this isn't the part I wanted to get to, but I'm just pointing out you can't. I'm just pointing out why there's an incompatibility here. I'm saying there's two completely different things. Okay? Force bits, moving the speed of light, and matter, which has no innate speed. It must capture force bits to have any momentum. It cannot move unless it has trapped force. All right, a good analogy is an asteroid in near miss with a planet. I'm just saying that's a horrible analogy. That's electrons on electrons. Okay, if you want to have two electrons interact, well, yeah, they're going to bounce off each other's radiation. Photons aren't radiating anything, and they're not being affected by any radiation. So you can't bend a photon with force. A good near miss with a planet where the planet changes the trajectory of the asteroid. No, it's a terrible analogy. It isn't happening that way. All right. So I've addressed that. I sort of addressed the Gerlach thing. I don't want to do the rest of the two slit. I mean, I didn't finish this other guy's two slit stuff yet. I mean, I did look at this stack exchange thing on head-on collisions with photons, and it doesn't indicate. It primarily indicates no, it never happens. So we obviously don't have any evidence of it happening. Photons hitting photons. So they're just, there's no evidence. They can speculate, but they can't. They have no experiment that ever demonstrates this thing happening. All right, so I think that's it. So then I can get to some of these electrical principles. All right, now as I stated in a previous video, this might be how some teachers actually might even say something like this. I'm not sure. So I'm not saying this is completely original. But I don't, like I said, I can't point to anybody who says it this way. But it's, I mean, you know, when I realized that this is how it works, I mean, it was just, oh yeah, that's huge. It's, you know, just as it's a minor way of explaining it, but it's just huge in understanding what's happening. So the idea, this difference between voltage and current, and the only difference is that all these exchanges are happening between atoms. Okay, electricity is what atoms do to each other. It's an atomic activity. You have to have the atoms to have electricity. You have to have electrons under pressure. They can't be free electrons and do electricity. They have to be bound to something. Now, they don't have to be glued to it. They don't have to be part of the atom, but they at least have to be interested in the atom. Okay. And what I've sort of explained is there's going to be an exchange. You're going to pump an atom up, okay? You pump one atom up, and it's next to a weak atom, and this is as soon as you have any imbalance between these two atoms, the electrons balance it out, and they say, let's just become this, and then that just cascades. This atom says you're this, then it blends it, and it blends it and blends it. So that's how the pressure moves through the wire. It's just pumping up an atom, and then that pumped up that amount of pressure is just dissipated through all the other atoms as long as they have lower pressure. Now, if we don't have a ground to go to, that is, we don't have a source of low pressure, then eventually they'll just pump up all the atoms and nothing will happen. Everything stops. There'll be no movement of the force. You can't pump voltage in, right? I can't put 4 pressure. You know, I got a bunch of 4 pressures, you know, this much, and I try to pump in this much. I can't pump it in because it won't go anywhere. There's no lower pressure for me to pour the water into. So it's like a bucket's full. I can't pour water into it. All right. And the other thing is this current idea. And all the current means is that that's how many atoms are involved in the process. So current just has to do with how many atoms are doing the exchanging. And voltage has to do with how big a difference there is in the potential. How much pressure you're pumping. 10, 9, 7, 4. It just has to do with how big you've made the atom. How much more pressure these electrons have on this atom versus the atom next to it. And that's the voltage. And the current is how many of the atoms are involved in the process. Yeah, so if you can decrease the voltage and increase the current, the idea would be, oh, so I should have said the important part. Obviously, when it's big, now it's a monopole. Now it's charged. It's magnetized, essentially. It's a magnetic monopole, the atom. So when it goes big, magnetic monopole, let's just say north. And when it's small, then it's magnetic monopole south. North, south. North, south. Plus, minus. And obviously, for there to be a cascade of this pressure, there has to be somewhere for it to drain. So there has to be the negative to compensate for the positive, to create the low pressure for it to go to. And so every time this stuff happens, there's not waste, but every time this stuff happens, every time they exchange, they leak. Okay, the stuff they're exchanging, the pressure. So they leak the pressure. Some of the pressure leaks out of this hose. So you have a hose, and it's just not a great hose, so it leaks. So the more atoms you can involve in the process, the more leakage you get, and the leakage is the magnetism. Okay. And all right. Yeah, so you can sort of understand there can only be magnetism when the current's moving, because you can only have leakage when it's moving. All right. When it's transferring between the atoms. And yeah, and so you can, and you're only going to create the magnetism if you are involving, the more atoms you involve, the more leakage you can create. So it's almost thinking about in the heat kind of way. If they're all a little bit inefficient and they all create a little bit of heat, and you wanted to create heat, then you'd want to have a high current and a low voltage. But it's just, I'm just using heat as a metaphor because it's sort of the same thing in the sense that it's radiation, but it's not radiation in the same form. All right, so I can go to the drawing here, I think. All right, so the field's being created. All right, so that's the interesting part. So we have the motor effect, which is the right-hand rule, essentially. And as I've sort of pointed out, I just don't know exactly how to draw these things, so I'm just going to do the best I can. I sort of point out that, say if this was your conductor looking down at it, so it's going into the blackboard or whatever, what's happening is this radiation is coming out, all right, in mixed, and very precisely mixed. That is, it's precisely red, black, red, black, red, black. Electron force, proton force. Okay, and it's radially coming out of the wire in that form. And essentially, so if I put two coils of wire, okay, well, let's see, if I coiled this wire, you could sort of understand that the field that's going to be created is going to be even, but it is a dipole field. So it's not like plus and minus up here. Okay, the field that will be created inside the coil, okay, of wire is just like the field for measuring the mass of the electron. It's going to be this even field, all right, where everything's going to be hit, like the other conductor, the current flowing, they're going to have this even thing, all right? It's going to be the even amount of this pressure from both sides at any location. So no matter where I go in there, it's the same pressure saying line up this way, like a magnet, okay? There's the same amount of pull on the blue as there is in the red, same amount of repulsion from this one on the red as the blue. So everything is so equal, and it's equal at any position in here, that if I put a piece of ferrous material in here, you could sort of understand that what's this field going to do, this perfectly symmetrical field. Well, the perfectly symmetrical field is going to tell every single little bit to line up like a magnet. They're all going to be staggered, of course. And the staggering thing is important to the idea of what creates this in the first place, is the fact that it has to be staggered. The magnets have to, the polarity has to be staggered because they are repulsive. So as soon as one atom goes up and there's another up atom near it, they're going to start repelling each other, which means they're going to move their position. So I'm just saying, as soon as you can sort of understand, this magnet, this thing goes, this one's positive, this one's negative. They're next to each other. When they equalize, they're going to hate each other, right? So they can't stay next to each other when they're equal. They have to stagger. So that provides the opportunity for the alignment of the magnetism. So they're never lined up on the surface. The surface is always this, which means when you're transferring the pressure, all right, it's there's always this dipolarity to it. So anyway, so when you have when you put the iron, the ferrous material into this coil, you can sort of understand that the magnetism isn't making, okay, the ferrous material magnetic, in the sense it's not creating the magnetism. It's just turning the material into a magnet by aligning all of the domains, lining everything up, north, south, north, south, north, south, because it's a perfect, just like the electron gets stuck in the circle in the other example. It's a perfectly symmetrical field. The symmetry tells all the compass needles to line up this way. Just every single one perfectly lined up inside the coil. So it turns it into a magnet, and a powerful magnet because it's dense material, and it's a lot of atoms involved. And so it creates a powerful magnet, where the coil wire itself doesn't have the same density. It's only making a little field out of the electricity, okay, and it doesn't have any pre-existing dipoles to put in positions. It can't just turn something to create magnetism. The only thing creating the magnetism is the imposing the voltage pressure and then letting some of it leak out. All right, so how else to say, what else to include here? So so as I pointed out, it's really the motor force just has to do with the fact that one side will have to always have an extra negative line on it, and one side will always have an extra positive, and because of that, one side will be perceived as a plus side, one side will be perceived as a minus side, and that's essentially the right-hand rule, is that imbalance. Alright, so and then you can sort of understand that the rest of it has to do with like charged surfaces, for example. So if I take a big surface and I put a voltage on it, that voltage doesn't leak out of it, you could argue, right? It just, so this is positively charged surface, a big piece of metal or something. And I can put 15,000 volts on it, and obviously every one of these little surface atoms will all be affected by that charge. I'd be back. Alright, I'm back. Where was I? Alright, charge. Yeah, so it's just a surface density thingy, you know, with charge, right? But the charge doesn't go anywhere. So clearly what it's doing is acting like a magnet, in the sense that it's a monopole magnet, in the sense that it's going to reflect any red energy that comes towards it. So anything that is the same charge, it's going to reflect it off that whole surface like a mirror. So it's going to behave like a magnet, and it doesn't need any energy to create that radiation, because that radiation is the same radiation that a magnet uses, which is the radiation in is the radiation out, where the coiled wire is leaking some extra radiation. So it's not just that it's magnetized the wire and the wire's creating some rays, it's that it's actually radiating some energy. But it's still a tiny amount of energy compared to the external energy's potential. So the external energy, if you can segregate all of it, has a tremendous potential in terms of the amount of energy that's actually going through us all the time. And you can see that in gravity, you know, that you play with it just a little bit of the force, you can create tremendous amounts of acceleration, differences in potential, and that's all it is. Again, differences in potential. This doesn't move until I create a difference in potential, and whether it's an electrical difference or a gravitational difference or a magnetic difference, it's all just a difference in how much usable energy or energy that the thing is sensitive to, red or blue, and then it moves. But it only does that because of how you can arrange the matter bits and how you can excrete the force bits from matter bits. All right, is there anything else I really need to say about that? Let's see. So if you're, I'm just trying to think if it matters just which way a current's moving and all that kind of stuff. Not really. You know, I mean, it just has the subtle motor effect change. So when you change the direction of the current, you just change which side is red and which side is blue. You know, this marginal difference. So that's why they need to use so much current to create such a tiny bit of magnetic effect in, say, 2 wires. You have to put in a tremendous amount. You have to activate every single atom in the conductor to get this little tiny bit of electrical motor difference, the difference that creates the attraction and repulsion in with DC current through wires. All right. So what else? Anything else? That's probably enough. Yeah. So eventually I'll do a step-by-step through this thing. It's a little, just complicated. First you have to do the atom pressure thing. Understand that electricity is an atomic function. And there's no electric field. There's just a form of a magnetic field, a kind of a magnetic field being created. And then the rest of it's just what you're creating the magnetic field out of, a big surface or a small surface. And all those things matter. So, charge density and such. I don't think there's anything else. Yeah, that's probably enough. Okay. Most of what I needed to say was in there somewhere, so we'll call it a video. And such. I'm gonna get more light on this thing, I guess. Really should be enough. Yeah, up the contrast, or maybe I can up the resolution a little. It's a little flickery. Anyway, till next time.